Hey everybody, and welcome to Proof by Contradiction with me. Today we're going to prove things by assuming both P and Q are true. Remember last time when we did contraposition, we assumed that not Q was true and proved not P would be true. And that was logically equivalent to P implies Q. And so we were able to just state the contrapositive, work from there, and prove that instead. Contradiction is a little bit more general because sometimes contraposition isn't enough. And so what contradiction does is it says, well, I'm going to say that P and Q is true and then work down to something that is ridiculous for some reason. So two types of situations where this is going to pop up. Number one, you've got a standalone proposition. Your book proved square root of 2 is irrational. You can't use contraposition on that because there is no if-then statement. There is no contraposition. What do? We already covered that we hate dealing with irrationals. So, contradiction. Another place that it pops up is P then Q. So we do use it for conditionals. And this is when we say P is true and Q is not Q is true. So what we're going to do is we take that and then we work with a series of deductions. Eventually, we will work to something that either contradicts the fact that P is true, contradicts the fact that Q is true, or is simply a ridiculous statement, like 1/2 is an integer. Like, no, it's not. So from there, once we've worked our way to something being ridiculous, we're like, oh, well, we said that Q was true, or not Q was true. Guess we were wrong. So Q must be, so if not Q isn't true, it has to be false. So if not Q is false, that means the original Q would have had to have a truth value of true. Warning, just gonna pre-come up with pre-say this. You guys might get confused and you're like, oh, which one's contradiction? Which one's contraposition? The difference can be subtle. Specifically, whenever you end up in this case, the difference is very subtle. But be sure, try to keep them straight. We will work on keeping them straight. Okay, so let's go ahead and try and prove some things. I'm going to start with the first type of case where it's just a standalone proposition. The book did square root of 2, and so I want you guys to be able to have different resources. So I'm going to do his close but obnoxious cousin, square root of 6. Because we are good people or good mathematicians, we are going to go, can we do this directly? Just like, don't know much about irrational stuff. I know it's not rational. Yep, okay, I've considered it. I can't do this directly. So I'm going to ask, well, why is it irrational? What happens if it's not? And literally that question, what happens if it's not, is where contradiction comes from. So we're going to say we're doing this by contradiction. And we're going to say, well, let's suppose that square root of 6 is rational. Yep, that's the definition. So then we apply the definition of rational. We say the square root of 6 will then be equal to P over Q. And then P and Q will have to be integers. Q can't be 0. Okay. So then we can say, we can square both sides. We can say that 6 equals P squared over Q squared. And then we can solve that. Sorry, running out of battery. There we go. we can multiply both sides by q. There we go. So then I see this and I'm just like, oh, that's even on one side. That means I can now conclude things about p squared. So let's rewrite that. Now the left side fits the format of, what is it? Even. We will acknowledge that this is an integer. And then while we're at it, we'll acknowledge that p squared is an integer too. So then we can say that p squared is even. And then from your worksheet last time, that means we get to conclude that p is even. All right, we're getting somewhere. It's kind of like, okay, now what? I'm like, well, we've said things about p. Maybe we can run with that and try and get some things about q. So we keep running. So then there exists k such that p equals 2k. Then let's shrink this down a little bit. So then I'm going to run with that and say 3q squared equals 2k squared. And I need more room. Let's run over here. So then we can write 3q squared equals 4k squared. Do a little bit of canceling with my 2. Get 3q squared equals 2k squared. Okay. So I know overall this has to be even because we are sitting here in the case of 2 times integer. What we can't do is we can't say, oh, well, 3 is odd, and therefore q squared is even. We don't have that tool. We can't use it. We essentially can prove it, though. Really easy. We can say, I need more information about q. It has 2 possible things. It can be even, it can be odd. Let's look at what happens in both of those cases. Case 1. Let's do q is even because that's the fast one. Q is even. So what happens if q is even? Sure, I can write it as 2 well. I can chase it after that. But what is the goal? What are we trying to do? We've got 6 is equal to p over q is a rational number. And like, I remember things about rational numbers. I can remember that I can write p and q so that they are most reduced all the way. Like I don't have to leave them so that I don't know, 4 over 6. Like why do 4 over 6 when I can do 2 over 3? So I'm going to add this condition to the front of my proof because I see that that would be helpful now, such that the GCD of p over q equals 1. So now back to case 1. We have q is even, we have p is even. So then the GCD of p and q is going to be at least 2. That means we have a contradiction because there's no reason we can't, there's no reason we can't write them or state at the beginning that they are in their lowest terms. So GCD of p and q is equal to 1. So that means q isn't even. Okay. And really, please come and talk to me if why I wanted or why I was able to insert this into my proof is unclear. It's a common trick. You're just like, hey, this is rational, blah, blah, blah about rational. Oh, geez, you know what? Maybe I should have made those guys relatively prime to each other. Go back, add that in, get a contradiction later. Okay. Case 2. We know why it's going to break. If q is odd, then q squared will be odd. Q squared times 3 will be odd. Odd equals even. We know that's what's going to happen. We can't just say, oh yeah, that's going to cause a problem. We are going to take the time and very meticulously prove it. So q is odd. So we say suppose q is odd. Then there exists, we already used k. So we're going to use L now. L. We're going to say L doesn't equal 0. Or no, L could be 0. Sorry, I was thinking q isn't 0, but as long as we're in odds, odds aren't 0, so we're okay. So there exists L such that q is equal to 2L plus 1. Okay. All right. So now that we have that, we can plug that in. Remember, we had 3 times q squared equals 2k squared. Let's go ahead and plug the q in, 2L plus 1 squared. So then that means we have, let's see, if we multiply the left side out all the way, we get 12L squared plus 12L plus 3 equals 2k squared. And then you could rewrite this whole thing as an odd and say you have odd equals even. That is okay. Another way to go at it is to say that like 12L squared plus 12L minus 2k squared equals negative 3. Factor out a 2 and say 6L squared plus 6L minus k squared equals negative 3. Then 6L squared plus 6L minus k squared is equal to 3/2. This is an integer, so we have a contradiction. And then just so that you could see the other way to have run at it, let's see, we diverged here. We could have done 2 times 6L squared plus 6L plus 1 equals 2k squared, and then been like 6L squared plus 6L plus 1 and k squared are integers. So then left-hand side is odd, and right-hand side is even. Contradiction. Okay, there's no right method for picking between going at it like that and going at it like that. Whatever your brain sees, just as long as you reach a contradiction that follows from taking logic steps. Okay, so then we have, from case 1, we have q is not even. We have from case 2, q is not odd. So then q is neither even nor odd. So q is not an integer, and that's a contradiction. Q is an integer. We assumed that. So there we go. We've got lots of contradictions in this particular proof. We had case 1, we were able to conclude that Q wasn't even. From case 2, we were able to conclude that it wasn't odd. We were able to put that together to make one big contradiction for the entire proof. So then that implies square root of 6 is rational. Otherwise, we get bogus stuff. Treating. So more intense than the square root of 2, but still very doable.
So that was an example of using a proof by contradiction to prove a statement P. Now, before we use it, proof by contradiction for proving like if-then statements, I kind of want to get into why this is going to work in a little bit more detail. What we're going to utilize is the fact that not P then Q is actually logically equivalent to P and not Q. Because if we think about it this way, then if we have P and not Q ends up being false for one of the reasons that we discussed on the very first slide, maybe we get something that implies that P is no longer true. And we're just like, but we assumed P was true. One of those sorts of problems. So if P and not Q is false, that means that not P implies Q is also going to have the same truth value of false, which means our original statement of P then Q would be true. And just to convince you guys real fast that these are indeed logically equivalent, I've got a truth table that we can run through very fast. So this first one, all we have to do is the opposite truth values. Which would work better if I did it correctly. Okay. And then we're going to do not Q. So flip all those truth values real fast. And then P and not Q, which is only going to be true if both P and not Q are true at the same time. So this is the only time it's going to be true. And then we can see that these two columns here are going to be the same, which means they are logically equivalent. So what you guys cannot do, though, for a proof by contradiction is assume not P and Q. This is not logically equivalent. Let's see. Just to convince you, not P is going to be false, false, true, true. And then not P and Q would end up being false, false, true, false. So right here, oh, not there, right here. Those don't match. They're not going to be logically equivalent. These ones are. These ones are not. So that's kind of, I think, the biggest problem you end up encountering with proof by contradiction. You end up putting the not on the wrong thing. All right. Now that I've talked about this theoretically for a while, let's look at a problem. Let's take this for a run.
We've got if n cubed plus 5 is odd, then n is even. I am going to be a good mathematician. I am going to give the direct proof a shot. We're going to say n cubed plus 5 is odd. Then n cubed plus 5 equals 2k plus 1. So then I can write n cubed equals 2k minus 4. And then we're kind of sitting here going, okay, well, I can't really say much about cube rooting both sides, so now what? And that's when you know, time to abandon ship. That was not the right proof method. And again, you don't have to be writing this down like in your homework. You don't have to say, I tried to do a direct proof and it didn't work. But I need you to get this train of thought because like when we hit the exam, you could probably do every single proof by contradiction, but that's bad form and I'm not going to let you. So you need to practice thinking like this. All right. So after, now that I've lectured at you, by contradiction. Okay. We're going to assume that n cubed plus 5 and n are both odd. That means that there exists a and L integer such that n cubed plus 5 is equal to 2k plus 1, and n is equal to 2l plus 1. So let's go ahead and sub that guy into there, because that's what the power of and gives us. They're both true, so we can substitute them. So we get 2l plus 1 cubed plus 5 is equal to 2k plus 1. And then we can multiply this out. How do I want to do that? We're going to do 8l cubed plus 12l squared plus 12l plus 1 plus 5 equals 2k plus 1. All right, let's keep rolling with this. Let's do, see, those guys cancel. Let's move him over and him over. So 8l cubed plus 12l squared plus 12l minus 2k equals -5. And I can see I can factor out a 2 from this side. So let's go ahead and divide by 2. Same contradiction as last time. This is an integer. So that means we were, we made a bad assumption. So that means n cannot be odd. Thus, n is even. All right. There is another proof by contradiction. I'm going to say it is a valid proof, but I'm actually going to say it is a bad proof. Why do you think that is? I could have done this proof by contraposition. And so if you can do, basically the hierarchy is direct proof, contraposition, contradiction. Contradiction is the lowest of the proof styles. And so if you could do it by contraposition, you should have gone at it that way. If we had done contraposition up here, thinking about that contrapositive statement, it would be n is odd, then n cubed plus 5 is even. And we know that would have been fairly easy to chase down. Write it as an odd, plug it in, regroup all your integers, get something 2 times k bar. We've played that game. We can do that one. So bad proof could have done contraposition. I don't know why contraposition always makes me think of ballet, but it does. But anyway, there we go. There's another proof by contradiction that was done correctly. But again, if you can do contraposition instead of contradiction, try it. Last proof. Let's try A and B are in Z. Then A plus B is going to be, if it's greater than 19, we're going to get that either A or B has to be bigger than or equal to 10. So let's think about that. What if we tried to go at this directly? Okay, so we have A is greater than or equal to 10, and B is greater than or equal to 10. No, that's the, sorry. Suppose A plus B is greater than or equal to 19. It's been a long day, I apologize. Okay. Then we can say A is greater than or equal to 19 minus B. You're like, well, I need to know things about B. Cases, maybe even and odd isn't going to be particularly helpful, so now what? Maybe I could like go through and list every number less than 19 and be like, okay, but how do you know? If B was bigger than 19, how do you know about A? She's like, oh, geez. I can't possibly list every number. Okay, so don't want to do it this way. Contradiction it is. Okay. Contradiction. So we're going to suppose A plus B is greater than 19 and A is greater than 10. Or A is less than 10 and B cannot write B is less than 10. Right, so that would be not Q. So A is less than 10, B is less than 10. Change the or into an and. So now that we have that, now we can start running with A plus B. What can I say about A plus B? Well, I can say that A was less than 10, so I could substitute 10 in for A. Okay, and then I know some B is also less than 10. So that would be 10 plus 10 equal to 20. But what was it that I was trying to do? It was something involving 19. I said AB was going to be bigger than 19. Well, that just says that 19 is less than 20. So I didn't get a contradiction. So that makes me sad. So what can I do with this? Well, I could be a little bit more specific about A is less than 10. I was not necessarily wrong to run at it this way. A is less than 10, but A is an integer. That means I can say things about 9. So I could say A is less than 10 means A is less than or equal to 9. And then same about B. B is less than 10. So then B is less than or equal to 9. I'm going to put that in parentheses and like, aha, let's try that. So then we have A plus B is greater than 19, and A is less than or equal to 9, and B is less than or equal to 9. Let's try this. So then we've got 19 is less than or equal to A plus B, which is less than or equal to 9 plus B, less than or equal to 9 plus 9. Oh, there we go. Oh, that's a problem. 19 is not less than 18. That is a thing that we know. So then A has to be bigger than 10 or B has to be bigger than 10. One of them has to be bigger than 10. There we go. Another proof by contradiction. This is stuff that should not show up in your proof. You should definitely erase it and get rid of it. It is not pretty and I don't want to see it. If you did it, I'm glad that you did it. It shows good thinking skills, but I don't want to see it. bad proof presentation. Okay, there we go. That's another proof method, another indirect proof method. Remember, we have direct proof is obviously direct. Contrapositive, not as good as direct proof, but it is logically equivalent to P than Q. So we will accept contrapositive even though it's indirect. And then we have another indirect proof, more general, is the contradiction proof, and we use him as a last resort. There we go. Talk to you guys all again later.